Welcome back. This is the final three. This is November 2018, paper 2. Welcome to the channel if you're new. If you'd like to leave a like and subscribe, that would help me out a ton. If you want to see the exam this particular question comes from, please look at the description below. And in the comment section below, please leave comments and suggestions for what you'd like to see in this channel going forward, because that would be really helpful for me. And if you keep tuning back to the channel next few weeks, you'll see some new content arriving, hopefully. Okay, so this particular question is on inequalities. It's a two-way inequality, m squared plus 7 over 4, and then you've got the 22 and the 32 here. So with two-way inequalities, the easiest thing to do is to split it off. So if I look at the left-hand side first of all, so we'll look at the left-hand side. So m squared plus 7 over 4. Okay, we're going to look at that first. So if you times it by 4, you get 88. And then m squared plus 7, take away 7, 81 is less than m squared. Now, this in itself is worth thinking about because it's a quadratic. So what does it mean that 81 is always less than m squared? Well, if you draw the graph of m squared or x squared, you'll see a graph looks like that. If you think about the roots that's going to happen here, you'll have 9 and minus 9, and then up here you'll have 81. Now it's telling you that 81 is always less than m squared. In other words, m squared is always more than 81. So everything to the left of here and everything to the right of there. In other words, anything where m is less than minus 9, or anything where m is more than 9. Okay, so you've got to remember that the square root of 81 is plus or minus 9, but this is always worth doing, testing values to see what happens. So you'll see that m is less than minus 9 and or m is more than 9. That's what happens on the left hand side. On the right hand side, we have m squared plus 7 over 4 being less than 32. So again, you're going to multiply 32 by 4, so you get 128, and then you take away the 7, so m squared is less than 121. Again, we're going to get a square root here of 121, so I'm thinking about 11 and minus 11, but let's have a look at the sketch of this. So here's the sketch of x squared. Here's minus 11, here's plus 11. Where is m less than 121? So it's less than 121 anywhere in here. So anywhere between the values, m between 11 and minus 11. So on the right hand side, we have m between minus 11 and 11. Now, if we combine our two regions together, so our two regions up here, we had m being less than 11, sorry, just circle that, m less than 11 and m more than 9. So the only values that fulfill that will be anything between 9 and 11. So that's one region that obeys, anything between 9 and 11. On the other side, on the other hand though, we've got minus 11 being less than m, and we've got m being less than minus 9. So another region that is being asked for is anything between minus 11 and minus 9, so anything between those two regions. So any number in this range and any number in that range. It's not asking for integers, so you can leave decimals, and decimals is fine. So this is completely fine now as two regions that satisfy. The common error is to write only one region, but you've got to bear in mind that this particular question is worth 5 marks, so it needs a bit more thinking. Question 20 is this question. It's about a frustum of a cone. Now, this is a very, very difficult question. Needs a lot of thinking. You get a lot of stuff going on, but it is a calculator paper, and the key thing here is to use your calculator well. Now, the strategies are important for this particular question, so I'll talk through what you do here. It's talking about a cone. It's talking specifically about a frustum that's made by removing a cone with height 3.2 from a solid cone. So they're always telling you, look, you've got a big cone, take a small cone away and you're left with your frustum. Okay, the frustum is joined to a solid hemisphere. So this hemisphere here is saying the density of the frustum is 2.4. So as soon as I see that, I'm thinking, all right, density, mass, volume. So I'm doing my little triangle just to make sure I've got it remembered. And then again, the density hemisphere, 4.8, so would be entitled density. This again, I'm thinking density, mass, volume. So the connection here is to try and think through, we've got to get the volumes of these things. The first thing to do is to get the volume of the frustum. So let's start with that. Now they're telling you that the frustum is created by doing the volume of the big cone, or the big cone, take away the volume of the small cone. So let's talk through how we do that. The big cone, take away the small cone. We're told up here in the corner helpfully what the volume of a cone is. The volume of a big cone and the small cone can then be constructed. So the volume of the frustum, so I'll just put volume of F. That's going to be the volume of the big cone. So that's a third times pi times 3.6 squared times 6.4. That's the big cone. And then from that, we're going to subtract a third times pi times the small cone. The small cone will be, because this is half the size, it's all going to be similar. So this will be half the size. So 1.8 squared times 3.2. Okay, so that's this expression to get that. Now, I'll leave as much as I can to one side for now, but if you use a calculator carefully, you'll get an answer for this, and it is well worth just working through that with your calculator. Now, what's good about calculators is, you know, they've got a pi button down there, so we're gonna use the pi button and work our way through. So what I'm doing now, just off camera, is I'm working out the decimal that goes with this. So I'm just cranking this all through. So this is I'm going to write down the parts. So this is the first part. So this is this bit up here. So the 86.858. This is this bit. So this is the volume of the big cone. I'm going to write it all down because I'd like to come back and check it afterwards just to make sure I've got it right. And then we're going to do the volume of the small cone now. So again, I'm just doing this off camera. So volume of the small cone. This is the volume of the small cone. So 10.857344421 ... So again, this is the volume of the big cone, volume of the small cone. I'm going to subtract those two things together or away from each other. 875.369. Take away this. That's going to be right. So this is the volume of the frustum. 76.001.409.48. ... That is the volume of the frustum. Now, we're told the density of the frustum. Density of the frustum is 2.4, so it would be quite good now for us to work out the mass of the frustum. So again, the mass of the frustum will be the density, this bit, times the volume. So these two things multiplied together. It's density 2.4 times this volume here, 7.76.00140.948, and that's again, something I can do it on the calculator. So you get 182. So 182.40338828. Okay, and grams. Leave it all as approximate as we can for now. We'll come back and round up later. So that's the frustum dealt with. Now we need to deal with the hemisphere. So the volume of a sphere is 4/3 pi r cubed. So this is a hemisphere. This is half. So we're going to halve this off. So half of the volume of a hemisphere must be 2/3 pi r cubed for the volume of a hemisphere. So again, I'm going to try and explain what we're doing. So volume of the hemisphere here will be 2/3 pi r cubed. In this case, it's 2/3 times pi times 3.6 cubed. So again, taking my time, I will show this to you. So I'm going to do 2 divided by 3, and then times the pi, and then times 3.6 to the power 3, 97.716. 0979. Okay, so quite a lot of stuff we have to get hold of, but that's the volume of the hemisphere. Now we're told that the density of the hemisphere is 4.8 grams per centimeter cubed. So I'm going to do the mass of the hemisphere here, so mass of H, and the mass will be this times 4.8. So 4.8 times this thing here, and you can do that on the calculator real quick, and I'm getting 469, so 469.037269 grams. Okay, so we've got, at this point, we've got the mass of the frustum and the mass of the hemisphere. To work out the density of the solid then, I do this mass and this mass added up, so these two masses added up, and then divide by the volumes combined. So this volume here, which we got from earlier, and that volume there combined. So the two masses divided by the two volumes. So the density of the shape S will be 182.4033828 plus this thing 469.037269, and then divide by, and it's going to be 97.7160979, so that's this bit, and then this bit, so 76.0014094. You can see why it helps to write down the numbers as you go along, because it saves a lot of work later on. And we do keep it nice and approximate at the moment. We don't round up until right at the end. That's the golden rule, so you don't make a mess. So it's important to get this right. You can use brackets and things in your calculators, which I'm doing right now to show you that, using brackets, just to save you some work, and you don't have to remember so much. So 76.0014094. Okay. And when you do that, you get 3, it's a nice easy answer, 3.75. And that would be grams per centimeters cubed. And that's your answer. That would get you your, I think it's 5 marks for this one. It was actually a whole nother page for working in this particular paper, but I managed to squeeze it in on this page. But the key thing here is to take your time and just take it step by step, and to write down the key things as you go, and then you'll be fine. Because as a calculator paper, you can write down all the horrible calculations as you go, and that saves you a lot of pain for later on. Okay, question 21, the last question of the paper, is this one. So this is a interesting question. It's a circle theorems question, but it's quite an unusual question. I don't think I've seen one like this before or since. So it's quite an interesting question from a variety of reasons. So it's talking about 4 points on a circle with center O, and then all the circles intersecting and straight lines. It's asking you to prove something. Prove that the angle CAB, that's this angle in here, is the same as this angle here. So this is quite an interesting problem, because it's clearly a circle theorems question, but what you've got to do is just look into your mind and think about the revision that you've done. So what circle theorems have we learned? We've learned about angles in a circle, in the center being double the angle at the circumference. It's probably not going to be that one here. We've learned about tangents, so there's no tangents in this question. We've learned about alternate segment theorem. Again, that involves tangents, no tangents here. And we've learned some other things as well, but fundamentally the one thing you need here is cyclic quadrilaterals. But you do need to do a little thing first. So we're going to draw a line that goes from here to here. And that line is the key that unlocks this problem, because then we have a cyclic quadrilateral, a four-sided shape here, cyclic quadrilateral. This angle in here, which I'm going to start with, this is the angle they want you to start with, CAB. Okay, we know this one here must be opposite to that in the cyclic quadrilateral. So if this is x, this is 180 minus x. It has to be. Now, looking at these two, this is on a straight line. So we can see that this is going to be x again. Okay, because it has to be, because 180 take away this must be x. I've created an isosceles triangle here because this is the center of the circle here. So this is a radius and that's a radius. So this is an isosceles triangle, and an isosceles triangle has two angles in the corner that are identical. So if this is x, this has to be x as well. And there I've proved that this angle here, angle CAB, is the same as ABC. You can see that proves it. Now, of course, all of that stuff I've just told you has to be written down in a way that the examiner is going to be persuaded. So we need to write some things. So we're going to say, let the angle CAB be x. That's what I started with. Then the angle CRO is 180 minus x. And we write down the reasons, cyclic quadrilateral, in the brackets. Then that implied that this angle here was x, so angle ORB is x, and we write down straight lines. So the examiner's told straight lines. Then we understood that triangle ORB was isosceles, okay, which implied in itself that the angle OBR is also x, okay, equal to angle ORB, and then therefore that proves that angle CAB is equal to angle ABC. Okay, so all of that very quickly written down, and you can see the logic. So just go through it once more. You start off with this line, there's the angle, this angle here is opposite to that in a cyclic quadrilateral, so this must add up to 180. This one here is on a straight line with this one, so this must add up to 180, so this one must be x. And then because we've created an isosceles triangle, these two are the same. So it's quite an easy proof once you look at it, but it's in itself quite a difficult question because you wouldn't necessarily think of doing these things, particularly adding this line here. So yeah, there's elements of it that I think are quite tough, but otherwise, it's once you get into it, it's fairly easy to understand once it's explained to you. Right, that's the end of November 2018. That was paper 2. Stay tuned because I'm about to do paper 3 and I'll be adding more content in the next few weeks. If you're revising for your exams for the summer, I do wish you all the best for those. Good luck and hopefully see you soon. Thanks. Bye-bye.